7.4, make sure that you write down the definition from your book. There is only one. And the first problem you're going to see is, for the given series, find and graph the partial sum Sn for n equals 1, 2, 3, 4, and 5. And they give you those. Here's where n is 1, 2, 3, 4, and 5. And all we have to do is pretty much graph them. And so we know that a half is 0.5. And if you just throw these in your calculator and divide them out, these are where the decimals are coming from. Okay, and so now on our graph, we're going to label this. Remember, this is your n-axis. So 1, 2, 3, 4, 5. And it looks like this starts at 0.5 and goes to 0.7. So I'm going to say 0.5, 0.6, 0.7, and 0.8. And when I graph these, I'm just going to estimate exactly, where they would go. And as you can tell, this graph here is kind of tapering off, and it stays right below this line. And so, and you can notice that right here, it looks like it's approaching 0.75, but it really never reaches it. So in the directions where it says describe what happens to the sequence as it increases, we're going to write approaching 0.75. All right, here's a very important rule for the entire section. We have S equals A1, which is still your first term, over 1 minus R, and R is that ratio. Now here's the most important part. There's only going to be an infinite geometric series if the absolute value of 1 is less than, or the absolute value of R is less than 1. If it's more than or equal to 1, the series will have no sum. So I'm going to jump right into an example. Notice how we do not have a number up here. This is infinite, so there will be no number up there at all. And remember, this 8 here is always going to be your A1, which is your first term, and the 1/5 will be your R. We're looking at the rate, the ratio. The ratio cannot be more than 1. And if you throw in 1 divided by 5 in your calculator, you'll notice that that is not over 1. 1 divided by 5 is actually 0.2. So it's well below the 1. Okay, so this is good. We're going to use that equation now because it will have a sum. And we're going to say the sum is equal to A1 over 1 minus the R. Okay, so when you calculate all this out, you're going to get it equal to 10. And that's your answer. Here's an example 2. It's the same type of thing. They don't give you the R in this case. You actually have to find it. And the way we find R is by taking this value and dividing it by the first one. Now, as long as you put parentheses around each one of these in your calculator, you will get 1.6 repeating. Notice how it's over 1. So this problem here has no sum. You don't even have to do it. All right, now the last type of problem says write the repeating decimal as a fraction in lowest terms. We're going to kind of set this up so that it looks like a pattern. And if you think about it, we have the number 22 with a repeating 2. So we have 22, and that 22 is in the hundredth spot. So if we multiply this by 0.01, because that's the hundredths, that's really how we would get 0.22. And then we add with another exponent of a 1, this is going to make the 2 repeating. And if we keep doing this over and over again, with the exponents increasing, we're going to get another 2 and another 2. So this is how we get this series going here. And so we're going to use this equation once again, and we know that A1 is 22 times 0.01. Right here. That's your A1. Now, 1 minus the ratio is going to be the 0.01, because that is what we're multiplying to the power of every single time. And when you do this out, we're getting 0.22 divided by 0.99, and it ends up being 22 over 99, which is 2 over 9. And the reason I got 2 over 9 is I hit math, enter, enter, and this is how I'm getting these fractions here. And so the decimal that is repeating as a fraction in lowest terms is 2 divided by 9.